In this video, we will see how to perform the analysis and design of a transmission tower in MIDAS nGen. So first of all, there are different ways of modeling the transmission tower. One of the ways is by creating the body objects. Another one is by using member tab. With the help of coordinates, you can create your members. Then we have a structure tab in which you can generate different levels and you can add information to each level. However, I wouldn't recommend the story, but we do have this grid line option as well, which could help you to at least model the horizontal information. And for changing the angle, you can use some CAD type of tools in the program. So I would be using another way of modeling, and that is importing a CAD file. So you can have a CAD file with you, 2D or 3D. Just import the transmission tower information. It should be a centerline data. You can scale it according to the unit system that is given in MIDAS nGen, and also it is going to be with respect to the unit system used in AutoCAD. Now these lines that we are able to see as a preview over here can be kept as lines, body lines, or you can convert them into members. So you can select the appropriate type of member from here and a section property that is predefined, or you can define the section property and assign it accordingly. Each member type can have a different layer, and you can assign different section property to each layer that you have imported in MIDAS nGen. So after we have imported all our data from the AutoCAD file, we can go ahead and assign some loads. So in the loads, you can apply the self-weight, and then you can go to the boundary conditions. You can assign the supports, and here let's go for a pin type of supports. So this is one way in which we can just model the steel part and perform its analysis and design. However, we do have another option in MIDAS nGen that can help you to generate the pedestals and isolated footings and piles below that. So let's see how to do that. These are basement type of members. In that, we have pedestal right over here. All we have to do is select the one of the members at the bottom. One would be good enough, and then you can put up a height. The pedestal will always be in the vertical downward direction, so like this, and we can choose the size of the pedestal over here. After we are done with the pedestal, we will move to the next part, and that is the isolated footing. So you just simply select the members, pedestal members, and you can give a size for the isolated footing. You can get a preview before you click on apply, and you can also modify the thickness right over here or later. Now once you have your information with you, you can move to the next part. Next part is to either go with a pile array or to perform the analysis and find out the forces. According to the forces, you can decide, according to the reactions, you can decide how many number of piles are required to be applied on this particular structure. So let us go ahead and do this. We have already applied the self-weight to the structure. Let us also see how to assign wind loads, because wind loads are pretty significant for an open structure such as this transmission tower or telecommunication tower. So here, the first thing you do is assign wind load. You can use the open area option, and you can select all the steel members that are created over here, and this is in the X direction. You can select similarly in the Y direction if necessary. However, this is a very symmetric structure, so it would simply be generating the wind load case for one direction, and that would be in the global X direction. Then comes the design parameters, which we define based on Eurocode. So yes, Eurocode is incorporated in MIDAS nGen. The total height of the structure is 47.5, as we have seen before, and here we can specify the common parameters, orographic effects, effects of neighboring high-rise structures, raising of displacement height, and structural factors can be auto-calculated as well with respect to the information we provide in here. So now we will move to the pressure and force coefficients. Here we have the option to select open or others and check on or click on this auto calculation of pressure coefficients. In this you can see there is structural elements, circular cylinder and lattice, etc. So yes, we do have such kind of a lattice type of structure with us, and therefore we will just go ahead and click OK and use the coefficient factor as 2 for the x and y direction. And you can also generate a report in a Word file format for the calculations that the program has done or the formulas that the program has used to get to certain pressure values. So we'll click on OK and close, and then we will close this again, and here we will make this 0 for the one direction since we are applying the wind load in the x direction only. So we'll click OK, and that is it. So in this way we have applied the wind load in the x direction. Now we will go to the boundary conditions. Earlier we saw that using the support option we could apply the pinned or fixed type of supports, which would be applicable if we have not modeled our foundation members. Now we have modeled them, so we will move to the soil support to simulate the soil beneath our foundation members. So we can select the foundation members and we can create the soil spring definition with the help of user-defined tool or Joseph-Ebal's equations. If we are using Joseph-Ebal's equation, you can see there are options like a linear elastic and compression only. Now the compression only would be required if you are sure to apply only vertically downward forces, but here we have the wind loads and therefore we would go for linear elastic, since because of the wind loads there would be tension developed in the soil springs over here at least. So we will move to the linear elastic. Using these equations, as we can see here, the allowable settlement value, the factor of safety, will simply provide the soil bearing capacity. So the soil bearing capacity is available with us usually in kilonewton per meter square. So we will modify the unit system before we open this command. And then we will put up the value in kilonewton per meter square. So let us assume that the value is 180 or 150, for example, kilonewton per meter square. After using certain formulas, the horizontal and the vertical spring stiffness values are calculated, and you can see them over here before applying. You can click OK, close, and then simply select all the foundation members. You will see a preview and then click OK. So in this way we have applied the soil supports over here, and now we can move to the analysis. So in the analysis we can use analysis settings when you can consider number of nodes or number of divisions between each element. Then there are combinations. Combinations can be automatically generated for steel as well as concrete members. We do have steel members. Simply click auto generate, say add, and we have all the load combinations possible as per the applied loads. So we have the dead loads, and we have dead load plus wind load in the x direction and then in the negative x direction. So that is it. We will also create load combination for auto generate load combinations for the RC foundation members. So here we have the foundation member load combinations using which the design would be performed. We can create our static case in which we have the steel members and the basement members with the spring properties and the dead loads and wind loads. Then we can move to the design part, and in the design part we have this option to generate groups automatically. There is auto generate design group option available in the program, so you can do that. Another thing, you can generate drawings for your transmission tower, and for that you would need story definition. Now application of story definition is not too difficult, so we will just wait till the auto generation of design groups is completed. In the case of auto generation of design groups, there are options to modify the way of or the prefix of your members. Also there are different levels of detailing for generating the design groups, and secondly, you can manually also generate the design groups. No need to use the auto generate option. So we can see over here now the information about the auto generated groups, and we will hide all the labels. You'll go to the structure, and as I mentioned about the stories, we can go to the story data and click add over here, click OK, and yes, we will move to one more information before we create the story data. We will say story control data to tell the program what is the ground level, but if you do not want to use the ground level, just uncheck this option, click OK, and then we can auto generate the story data using all the information that we have with us. So we have all this data available with us. Just we'll click OK, and that is it. Next, we will move to the analysis part now, and we will run the analysis, but you can also go ahead with the design, generate a design case using the analysis case, and then you can run everything together. If you want the program to provide you with the reinforcement arrangement for your RC members, then you can check on this option, and you have further more details available to input as per the Eurocode, like the rebar data that you would like to specify or available input information from the site. So right now the analysis is being performed. It's completed. Now the design is getting performed. And that is also completed. Okay, now let's take a look at the analysis results first. Here we can just use this analysis tree menu, results tree menu, and double click on the information that we would like to check. Then at the ribbon menu at the top, you can see there is option to check on deform. We can see the deformed shape in this way. There is a legend that can show us the value of displacement. Maximum displacement is 3.02 mm for the static self-weight. And if you would like, you can check with the wind load as well. This is Z displacement that we're looking at, which is 13.87, but if you just make XYZ, then you'll get to see that maximum displacement is this we will change to wind load. Yeah, so the maximum displacement is 233.25. This is probably because of the X direction, so you can see it's more deforming in the X direction, and in the Y direction it's not much. Z direction is 13.87. So this is about the wind load output generated by the program for the deformed shape, and you can also choose how much you would like to scale it up and down, and if you would like to see the values, maximum only or all the values on the screen, and so on. Further, you can look at the reactions at the bottom. No need for deformed shape over here. You can see the maximum reaction that is in the Z direction. However, this is not the single location that we're talking about. It is, however, it is at the node, which is exactly at below the pedestal. What we need to look when we apply the soil springs is the subgrade stress. So you can see the pressure in the Z direction. You can change the unit system to kilonewton meter for understanding the data more easily. You can see the output for the combination of steel or combination of RC, and you can look at the maximum value over here. So at the max, 73.72 is the subgrade stress that is obtained by the program. Now what we can do is we can go to the pre-processing mode, and we can go to this member tab, and we can use pile array tool. In the case of pile array tool, you can assign a pile by using a spring set, and you have probably several types of pile types with different pile capacities. You can use a database available as per Korean and Japanese standards, or you can uncheck this option and inform in all the data manually as per the information available with you. So what I'll do over here is I'll use a cast in place pile with diameter of 500, and everything is already there with me now, and all I have to do is talk about the pile pairing capacity. So the compression capacity is probably 1000 kilonewton, and in the uplift capacity I'm using 100. Further, the pile spring constants can be calculated using code based option. We have Korean standards over here. The formulas are already given for the cast in place. You can see these if you're okay, or go ahead, or you can use the manual option, which is always available in the program. Now after this is done, we can go ahead, tell what is the head condition, and if it is a fixed or a hinge type of condition, and what is the soil layer. You can have mixed type of layer, or sand layer, or clay layer, and after that you can go ahead, provide the SPT value over here, and you can get the data available right over here about the information, and just you can click on OK, and after that you can see over here the option for check pile support. So that is one option, and the other is the pile calculation. So in the case of pile calculations, we can go ahead and understand if we can use certain output. So let us check RC root combination with maximum output, and we will view the results. Alright, so the sum of reactions that we are able to see is 3012, and we will be able to get that information with respect to the vertical pile capacity. So if we have the vertical pile capacity known to us, we can get automatically the number of piles required by the program. Now let us take a look at the design results. After we perform the design, we get to this design results tree menu, and we double click on the status to find the information like which members are passing, which members are failing, which are economical, which are critical, and which are uneconomical. So this is how we are able to see that the cross section is definitely not good enough for the design. We can also look at further results, such as was this total status with respect to was the failure with respect to the strength check, or was it because of the serviceability? So we can see from the strength check that the design results are pretty uneconomical, but we need more bigger size in case of the main columns or main beams at main elements at the edges. So we can further go ahead and understand if it is actual failure, or bending failure, shear failure. There is a punching failure check as well available for the foundation members. So we can see that there is major actual failure in this in some of these members, and we can modify the cross-section sizes and run the analysis and design again. And this is very easy to do. You can also go ahead and use the design report generator, select any member or element, and you can get a summary output in the form of Word file. So this is the Microsoft Word file. We can see why a particular member is failing. So there is a deflection failure, and it's 1.395. That's how much it is failing. And there is fatigue check as well, in case we have asked the program to do so for certain members. So that is about the summary design report. Now let's take a look at the detailed design report. So we'll take the another element or the same element, and you can just click OK to generate the Word file for detailed design calculations. So we get details about the inputs, about the forces at each part of the element, and then we also see that there are some factors, the parameters specified by the program, formulas are mentioned, and so on. So all of this information we can get it from the detailed calculation report itself. Apart from that, we can get to see the output in the form of tables by going to the steel section and going to the type of member that we have used in this entire structure. So this is for the steel. We can find out what is the exact reason for failure, and we can also see over here about the options available to modify the cross section, to help us to modify this cross section. So that is it. We get the information in terms of group members, or we can get it for every individual. Now, to rectify this entire structure, first of all, I will generate the groups such that the members that I need are into one group itself. The members that should have the same section property will be put under one group. So for that, I can simply go ahead to the design tab and design group directly, and I can select the type of element. So here I will go ahead and make use of certain selection tools that are available in the program for doing the selection. Like there is only front selection option, there is select all, there is unselect all, and so on. So we'll go ahead and do the selection of members. We'll give it a name, main beams, and we'll go ahead and select all of these members. We can also select in this way, or we can select it part by part for this entire structure. So this is how we can simply select. You can use some auto rotation tools with the help of control button. Likewise. So once this is done, we can get the information under the design tree menu. So let me go ahead and for now click on apply. Once we click apply, we can go to the design tree menu, and here we can see design group steel. In that we can see there are some design groups generated by the program, and you can also find a design group that we have manually generated. So we have at the end over here the main beams design group. So this design group contains all of these members. This would help us to also do a lot of information, like we can rename them, or we can select all of them by clicking, and we can modify their cross-section properties from the list that is available, or we can generate the cross-section properties and apply. So after this is done, then we can go ahead, perform the design, and then we can get the better output. So I would be doing this and getting back. These are going to be diagonals of our structure, and for them we can even use the drag and drop feature to assign the property. We can view the color of our structure with respect to the property that has been applied. so it is clearer for us to understand which of the members are yet to be modified. So in the end, we have main beams group, we have a group for the redundants, we have group for the diagonals. Now let's go ahead and perform the analysis and design. When we are performing the design only for the steel members, we do not need to ask the program for auto rebar arrangements. If we have applied our own reinforcements, then as well we don't need the program to modify it, just check it. So analysis and design is also completed. We can double click on the status and check the result. Okay, so I have provided the groups in this order. You can check in the design tree menu the design groups for steel, and we have created one design group for the column type of members, which are our mainframe members, and we have converted the diagonals into brace type of members, and these are the groups that we have over here. One is for the diagonals and one is for the braces. So in this way we could manually modify the information as well as change the cross-section property so as to check if members are passing or failing. We have applied 150, EA 150, 150 by 12 for the mainframes. Then for the braces we have 90, 98 and 150, 75, 15 for the diagonals. So yeah, so we'll go ahead now and we will run the design of the newly created groups, and for that purpose we will go to the design tab and create a new design group which would include the new group information. Anytime we modify the model file, we need to check if we have created information necessary for performing the analysis and design. So we need to generate load combinations to create a design case, and therefore we'll go to design auto generation for steel and auto generation for RC. And we can notice over here there is no load combination for the fatigue. So in case you would like to check the fatigue, it requires you to have a live load case. So since that is not there, there is no fatigue, and therefore no fatigue check is applied in this particular model. Okay, after this we can go ahead and create a design case wherein we can see now the load combinations and the new member groups, and then we'll go ahead to run the design. You can check on this option for rebar auto arrangement since now the forces are modified, and therefore the final reinforcements at the bottom would also require to be changed. Okay, so after the design is completed, we can now check the total status, and this seems like all the beams and columns or the brace members, except some of the brace members still require modification. We can probably change the cross-section size one more time only after we understand what is the reason for failure. So we will take a look at the status for the strength check, and here we can see there is a failure in strength check for these members, and the reason could be the combined ratio. So yes, there is a combined ratio issue. There is a high actual ratio, and if we combine it with the bending, there is a bending failure also. So if we combine it, then it will definitely be higher than 1. So that is why the combined ratio is failing. Other than that, the foundation members are also passing in the strength check. We can go with the serviceability check, in which we can see that there is failure for the bearing capacity ratio and overturning ratio, and also the sliding ratio. So it's pretty high as compared to what we had notice. So we can always go to the design report and generate a detailed information about the RC members as well, RC Foundation members also. Now after the design and information is completed, we can take the entire structure into MIDAS drawing for generating the details of our structure in the plan as well as elevation. So this is a detailed information about the foundation design. There is overturning taking place. The capacity seems to be pretty small as compared to the information required. So this is probably because we haven't mentioned the depth of the foundation below the ground level. So once we do that, definitely this could get rectified. Okay, so with the modifications and appropriate design solutions, we can initialize and go to the output to generate the drawings. So these are the settings. First of all, we will auto-generate the information and click OK, and then we will use generate drawing tool, which will open MIDAS drawing software, and at the same time it will import the structural information in MIDAS drawing itself. So once we have this information, we can go to the generate drawing and we can generate a structural plan. So this could be our foundation plan, or this could be at any level the floor plan which we had defined at the beginning using the auto generation tool in the story definition. Once all the information is collected by the program, it will be very quick to generate the section plans and elevations as well. We can place this particular foundation plan anywhere, and we can see over here these are the details which we can identify, like the reinforcement arrangement for the foundation members, and we can also generate cross section. So let's make a cross section wherein we can see the entire entire structure from the front. So we'll make a straight cut line at the start. We'll right click and we'll include at least the up to the center of the entire structure, and then we can place this cross section, and this will now display the front elevation of our transmission tower. This has all the information about the group, and each group will have certain cross section property which is also enlisted in this at this location itself. We get to see the levels at the same time, and in case this information is not required in 1D in one single line, you can always change this information using the structural drawing manager. So this is where you can modify the steel data if you want a single line or you want a double line. Likewise, you can specify and generate the elevation again. So after we are through with generation of the plans and elevations, we can always go ahead with the rebar arrangements as well. That would be mostly for the RC members, and we have already seen the foundation member information. In the case of pedestals, we can generate the information after its design has been completed. So we will move ahead to the next part, and that is the bill of material which we have for our steel members. You can generate it for center to center, and you can generate for basement as well, and this will create the quantity in the Excel file format. So this is the Excel sheet wherein we get the bill of material for each type of member, and the quantity is such that we get total length, unit weight, total weight, and the perimeter, outer surface area for painting, and we get a summary as well at the bottom. So basically we are interested in the total weight of the steel, which is given in ton over here, and this we can apply with certain scale factor to account for any additional bolts and also gusset plates, and then we can get the total price of the construction of the material by simply multiplying this with the rate of the steel available. This is steel type 1 for center to center, then this is steel type 2, which is based on the panel zone effect, and then we have RC basement, wherein you get separate quantity for the concrete and for the reinforcement. Concrete is in meter cube and reinforcement is in ton, again steel, so you can add this quantity as well into it, and this one as well. Furthermore, you get the formwork required for these members too in meter square. So that is it regarding the application of transmission tower using MIDAS nGen.